Hey guys, this is Sakshi back and I welcome you all to my edutech platform, Way to Learn. So before we go into the video, like my videos, share and subscribe my channel and do not forget to hit the bell. So let us go into our video which is from quantum mechanics and part 8. So in my last video we were like about to know about the wave function, operators used and so on. So in this video we'll be focusing on the important points on wave function and few formulas. So first point, the quantity psi of r comma t. Here r is in 3 dimension, the position, and t is the time. So the quantity wave function, which is a function of position and time, must be continuous. So this wave function must be continuous. Because if I say that the particle is moving in the form of wave, then obviously the wave should be continuous. It can't be like it can't stop at a point and then again continue at a point, because that particle is moving and it has a particular wave which it emits. Okay, so that which it moves in. So that wave function cannot be like split in between. So that wave function must be continuous, and also its partial derivative must be continuous. So this will be helpful in our formulas. So the quantity which is wave function and its partial derivative must be continuous, because only then this makes the wave function smooth. That is, the partial derivatives makes the wave function smooth in our graphs. So second point is that this quantity psi star psi theta, we'll learn what is this. So this quantity must exist. Say if I have a particle and I have a wave function regarding it, so that wave function should satisfy this psi star psi theta, and that must exist, and that should be a single value. That is, my wave function should be a single value. My wave function should satisfy this quantity psi star psi theta, and it also should be single value. So what do I mean by single value? So let me say that in this first graph you can see where I have marked x, right? So you can see that if at a position x1, so I can say now I am looking at the position x1, my wave function has like psi 1, psi 2 and psi 3. How can I have that? At a position x1, there will be only one wave function, one value of a wave function. It cannot have these many values of wave function. So that is what a single value means. So in the second graph, you can see that at a position x1, my psi value will be only 1, that is psi 1. So at a position x1, wave function will be 1 and it will be single value. So I hope you just understand what is single value. So let us see next point, where the wave function must be finite everywhere. So it should not go infinity. So it should be finite everywhere. So if I say that I have a wave function and in the place of x, I have substituted like, let me say my wave function is 1 by x. Okay, and it should be finite everywhere. So if I put x tends to 0 or x is equal to 0, obviously my wave function goes to infinity. So this should not happen. I can directly say that my wave function is not finite everywhere. It is infinite at a point x is equal to 0. So we'll learn about that later. So you have to know that wave function must be finite everywhere. So if my wave function is infinite, goes to infinity somewhere, then it is not valid over there. So you always do not use that particular point where it goes to infinity. So you can say that the wave function is not valid at point x is equal to 0 when the wave function is equal to 1 by x. So let us see the next point, where the wave function must satisfy the boundary conditions of the quantum mechanical system it represents. So we'll be learning many systems later on, like particle in box, simple harmonic oscillator, hydrogen atom, infinite well, tunneling effects, all those. So there are many systems in which the wave function will be having some constraints and it will have some boundary conditions. So it should satisfy those boundary conditions as well. So next, these 2 points are kind of a formula. You can note down this. the wave function must be normalized. So from minus infinity to plus infinity, this quantity psi star psi d tau should be equal to 1. When it satisfies this, we can say that my wave function is normalized and it should be normalized. So our wave function should be normalized. Okay, so if it is not normalized, then you have to do something so that we can normalize it. It should be equal to 1. We have to bring somehow it to be equal 1. Next will be the wave function must be orthogonal. So the wave function should satisfy the other relation, which is from minus infinity to plus infinity. The integral of psi star psi d tau should be equal to 0. So that is what is orthogonal and normalized. So when a wave function follows these two, I can say that my wave function is orthonormal. It is also orthogonal and it is also normalized. So it is an orthonormal wave function. So next important point, you just have to note this down. While solving problems, we'll try all such kind of problems which will help us, like, in order to understand this position probability density, how to solve them easily. Okay, you might not find it easy now, but it will be very easy after solving few problems. So when we do our problem session, we'll be doing many problems from position probability density so that you gain a confidence in solving these integral functions and also like normalizing the wave function very easily. So normalization will be a part in which we will carry out in a problem. You will learn that from a problem rather than doing it theory. So the position probability density, I have also written this in the form of Bryan ket vectors. So in Bryan ket vectors, you can see that psi, bra of psi and ket of psi should be equal to 1. So this will be the form of the position probability density in vector form. Okay. Now in scalar form, I can also say that P of r comma t is equal to psi star psi. Okay. So this quantity, I can also write the psi star psi as mod of psi square. So this quantity mod of psi square is the probability of finding the system at a time t in a volume d tau. Okay. So now on integrating this quantity, it should be equal to 1. So this is an important point where this quantity should always be equal to 1. Now, if this psi does not satisfy this condition, I have a psi, and after doing the square of it and integrating, I do not get 1. Then what should I do in order to get this condition satisfied? So, one can multiply the psi by a constant, say n. So it will become n psi. Okay, so now if you have psi which does not satisfy this condition, then you have to multiply the psi by n, a constant, any constant. It can be n, it can be a, it can be b, anything, whatever you choose. So it should be a constant multiplied to this wave function. So it will be, now this equation about the just psi square d tau will become as n square psi square d tau. And after doing this, we'll be learning what is normalization, other stuff in the problem while we do our problems. So, but this will be the equation later after we try to multiply this quantity psi by a constant n. Now, this probability current density is an other important formula. Sometimes you just have that equation just to find the probability current density of the given wave function. So just note down this formula, which will be very much helpful. And also this J, which is the probability current density, satisfies the equation of continuity. Here del dot J plus dou rho by, sorry, this is not rho, it's dou K by dou T equal to 0. This P represents the probability density over here, and J represents the probability current density. This is also similar to the same equation of continuity in EM, electromagnetic theory. So let us go. These are few important points for you to note down. So please note down. Now next, this is a very much important topic, the expectation value. So the expectation value is nothing but the average value of the variable. So if I say I have the variable to be an energy, like I can assume that it is a momentum. Okay, my variable is momentum. So that is operator use this momentum. So if I want to take the average value of that momentum, like I have a system in a particle, right? The particle is in the system, so I'll have some momentum operator to act on the system, and I'll get some values. So as I make measurements, the particle may change to other energy levels, and it can have various values. So in order to take the average value of all those operator which acts on the wave function, we use this expectation value, which is also called as an average value. So we use this particular formula in order to find the average or the expectation value of an operator when it operates on a wave function. So this is an important formula. Please note down where the expectation value of an operator is equal to minus infinity to plus infinity psi star A. A is the operator here. We can put an A cap over there. So psi star A psi d tau divided by minus infinity to plus infinity psi star psi d tau. So in this, like in the denominator, you have minus infinity to plus infinity psi star psi d tau, which is equal to the probability density, right? So I have said that every wave function should satisfy this equation, and it should be equal to 1. So before coming into the expectation value, before like finding out the expectation value, you can directly like find out the probability density if it satisfies equal to 1 or not. So when it satisfies equal to 1, you do not have to solve this denominator part because you will have already solved it. You just have to directly put the value for what you have found. If it is not normalized, you will put the normalized value. If it is normalized, then it's easy. It will be equal to 1. Okay. So just remember, like if I every time say that a wave function is normalized, I just say that this probability current density will be psi star psi d tau. This quantity will be equal to 1. That is what we say our psi to be normalized. Okay, now in bra and vector, that is the vector form, you can say that the psi A and psi, that is bra vector operator, and again the get vector divided by the probability density in vector form. Okay, so this is also in a vector form and this is in a functional form. We can find the average or expectation value. So this is an important formula. Now next we are going to learn something more important. Can be confusing, but it is much more important, and it will be very much helpful for you while solving problems. It can be kind of trick, but it is kind of confusing. So let us learn if you are going to learn this for the first time. But it will be easy when you solve problems. You will learn that. So eigenvalues are the expectation value for individual states. So what does this say is that we know that an operator operates on a wave function and gives us the eigenvalue, and that eigenvalue gives us the result, right? So if I say that I have used the energy operator and I have operated it on the wave function, I get an eigenvalue and again the wave function. So that eigenvalue gives me the information about the energy. So it is the same over here for the expectation value. Now if I have to find the expectation value or the average value for particle, if the particle is to be in energy E1 or E2, I can directly use the eigenvalues over there. So these eigenvalues can be helpful for me in order to find the expectation value for the individual states. So if I say I have to find the expectation value of my uh, energy in the state E1, I can use that eigenvalue of that energy E1 and I can just give the result to them, right? So this is very easy thing when you solve the problem. It will be like a few seconds work. So let me prove this. How do we use that? So let psi be C1 psi 1 plus C2 psi 2. Just an assumption. Then we have to find the Hamiltonian, the expectation value of the Hamiltonian. So we have to write this in the form. I'm not writing in the function form. I'll just write in the vector form because for me this vector form will be easy for you to make you understand. In the function form, I'll do problems. We'll do problems in the functional form. We'll learn that. But for this particular proof, I'm going to use the vector form. So my ket vector, like ket of psi, can be written as C1 psi1 plus C2 psi2. You can see that my ket vector do not affect the wave function. It is written as it is. Okay. Now my psi vector here. Now if you see, psi vector is the transpose conjugate of my wave function. Right. Now C1 and C2 are constants, but they can also be imaginary. They can also be complex. So these constants are like conjugated for the bra vector. So my bra vector form is written as this. Now we have ket vector and bra vector with us. Now I'm going to normalize this. We basically know that it should be equal to 1, but this is just a small thing that we have to do every time for the first few days, so that we just learn that, so that we get strong in that. So now we have to normalize this wave function. So I have written my bra and ket vector. You can see that. So C1 star psi1. Okay. Now I am going to use my distributive property and I am going to multiply these two brackets. So on multiplying them, psi1 or this psi1 and psi1. Okay, I have written all these. Now you can see that these two, that is psi1, psi2 and psi2, psi1 goes off. These goes to 0. Why? Because I have told that my wave function is orthogonal, right? So only when psi1 and psi1 operate, it will be equal to 1. But other than that, it will be equal to 0 because they are orthonormalized. My wave functions should be orthonormalized. These are the important points of the wave function, which I have already told you. So my wave function should be orthogonal and it should be normalized. Therefore, in order to satisfy that particular thing, here this psi1 and psi2 quantity goes off to 0. So now we have only two quantities left. C1 star C1, psi1 of psi1, C2 star C2, psi2 psi2. So now I know that they are normalized. Therefore, I can just directly put them to 1. Now this will change to C1 square plus C2 square. This is similar to that psi star psi. So I can directly write them as mod of C1 square plus mod of C2 square. So now I have taken only C1 psi1 plus C2 psi2 as my wave function, but sometimes it can have many wave functions. So I'm just writing this in my generalized form, that psi1 of psi1 should be equal to coefficient square, mod of coefficients of square. Now we know that this quantity should be equal to 1. So you can directly put them into 1. But if they are not equal to 1, then you will have to normalize that. We will learn that in the problems. So, but this is an important thing, just note down. So, next, remember this h psi is equal to E psi. When Hamiltonian operates on a wave function, it gives the energy eigenvalue. Because we can say that the Hamiltonian is the total energy of the system. So, it gives the energy as the eigenvalue. So, that will be our information. So, now, I'm going to find the numerator part. So C1 Psi2 and I have H in the middle. So what does this H do is, H operates on the ket vector. It does not operate on the bra vector because here you see H into psi. So it operates the ket vector. So I'm going to again use the distributive property over here. So you can see I have H psi1, H psi2 ket vectors. So now we have after operating them, I know that h psi will be equal to E psi. So h of ket vector will be equal to E of ket vector. So I'm going to just write that here. So C1 E1 psi1 plus C2 E2 psi2. That h will, after measuring, like after operating on the wave function, gives us the eigenvalue. That is what is written. So now using the distributive property again and using the orthogonal property and normalization property, I am just putting few quantities to equal to 1 and equal to 0. So you can note that down. Now, if you see, the remaining thing that we have is C1 square even C2 square even, right? So it can be mod of C1 square even plus mod of C2 square E2. Now I have my denominator and numerator part. I'm just going to use it over here. Cn square E1 plus C2 square E2 by the general form of Cn square. So I can also write my numerator in the general form, which is given as this. So now I say that the expectation value of h is given as this, and I have to find the expectation value, like the average value. Then I can use directly my eigenvalues. So because the expectation value is directly equal to the eigenvalue over here, h is directly equal to En. Only we have coefficients over here, but as we see, h is equal to its eigenvalue. So now if I say that what is the probability to find the particle to be in the energy level even. So now I can directly use only even part. I am collapsing again over here. So I need to find only even part. So I am going to consider only the coefficient of even and the denominator. So the coefficient of even divided by the denominator will give me the probability of the particle being in the energy level even. So this is also something confusing but will be helpful while solving problems. So we'll learn that. Okay. So in general you can write any operator A can be written as the coefficient mod of the coefficient square an divided by mod of the coefficient square. So that's all for this video. So thank you. Like my videos, share my videos, subscribe my channel, and also hit the bell. So see you in my next video. Ta-da!